Welcome to Chapter 20, where we will be talking about organic chemistry, and we're going to start with the structures of organic molecules. So organic chemistry and organic molecules is focused on molecules that contain carbon. This isn't basically carbon and oxygen compounds like carbon dioxide or carbon monoxide, but that's pretty much it. Anything else that contains carbon. And so carbon is very important, very unique, because inorganic compounds are, and every other compound that doesn't contain carbon, right? So there's over 100 atoms. We have focused on this, or sorry, 100 elements. We focus on this one element that's kind of the most important. And why? So organic, this term comes from the fact that basically the molecules that make up living things are made of carbon. So that's one of the reasons why we focus on it and kind of the motivation for the naming and kind of history as to why we've studied this. So why do carbon atoms why is that the kind of currency of living things, of molecules and living things? And the reason is there's kind of twofold. One, carbon atoms readily form 4 bonds. So that's good kind of as a structural building block. And they're really good at forming bonds to other carbon atoms. So you can make molecules that have shapes like chains. You can have branched chains, so you can kind of start to get into different shapes, different literal physical structures of the molecules, which you can use to make structures of living things, right? The kind of shapes of the molecules can reflect the shapes of, tissue, organs, stuff like that. And also one of the things that's really unique about carbon is it's one of the few atoms that you can form cyclical chains of, that you can kind of get these complicated structures that have a lot of variety to them. So there's a lot of different types of organic molecules, and there's a very rich kind of chemistry associated with these molecules that no other type of element can really do like carbon can. So in terms of living things, there are 4 primary biological types of molecules: carbohydrates, lipids, proteins, and nucleic acids. These are structures and shapes of these molecules that we'll kind of learn how to interpret as we move forward here. Not proteins. That's a really big molecule where you just abandoned any representation of the atoms that are in that molecule because there's thousands of atoms in there. So it's a really big molecule. But the important thing is that all of these are based around carbon and maybe some other flavors like oxygen. There's hydrogen in there. You can see phosphorus, nitrogen showing up in these nucleic acids. These organic molecules really do kind of have a lot of different size variations. Carbohydrates are pretty small molecules. These proteins are massive. In addition to biological applications, organic molecules also have a lot of applications in kind of commercial use. So for example, molecules, here we have a couple different representations: caffeine, Kevlar, acetaminophen, and polyethylene terephthalate. All of these are organic molecules. They're all based around carbon as the primary molecule. You'll note in some of the cases like caffeine, there's a lot of non-carbon atoms in here, but it still primarily is carbon that's kind of holding it all together. These range from things. Caffeine would be, a kind of consumer good that we eat. Acetaminophen is a pharmaceutical. Kevlar is the main material in bulletproof vests, so kind of a protection. Polyethylene terephthalate is the main kind of plastic that we use. So these organic molecules have wide ranges of applicability, from everything of things that we eat, things that medicine is all organic, primarily organic molecules, structural materials, kind of functional, very, very functional materials like plastic. So there's a really high utility and a lot of different types of properties you can get out of these compounds. And so there's a lot of rich chemistry. That's why we study it as its own kind of special world, organic. So we want to spend some time talking about the structures of organic molecules. And one of the things that's special is that there's really not a lot of variety to the atom types that show up. Carbon is going to be in there. Hydrogen is another main thing. And then after that, nitrogen, oxygen, phosphorus, sulfur are the main other things you would see. And then potentially the halogens. You'll see halogens also popping up in your organic molecules. The thing is, when you're looking at atoms in these types of organic molecules, they're generally always all going to obey the octet rule, and they're going to generally be kind of well-behaved, if you will. So carbon atoms are always going to form 4 bonds. Hydrogens only form 1 bond. Carbon atoms are going to be kind of your backbone atoms that make up the structure of the molecule, and something like hydrogens and the halogens are going to be kind of the decoration, outer atoms. They only form 1 bond, so they can't be kind of structural. They have to be kind of caps. Nitrogen and phosphorus phosphorus have 1 lone pair and 3 bonds. And then sulfur and oxygen will always have 2 lone pairs and 1 bond. So we won't have any expanded valence. We won't have any kind of fancy oxygen forming single bonds or anything like that. It's going to form, most of these molecules are going to be very well behaved. So let's look at some examples of drawing Lewis structures for some small organic molecules. Let's look at ethylene, which is C2H4, formaldehyde, CH2O, and formic acid, which is CH2O2.
All right, so we want Lewis structures for some different compounds. It's going to be based on our formulas that were chemical formulas. So ethylene is C2H4. And so one of the ideas with developing Lewis structures for organic compounds is we can just eventually just kind of develop some kind of senses of number of bonds atoms have and kind of typical structures. But we can also always rely on kind of our general rules that we have established so far. For example, the number of valence electrons in our compound, kind of the total electrons we would have. So we know we have 2 carbon atoms and we have 4 hydrogen atoms. So that would mean each carbon is 4 valence electrons. Each hydrogen is 1 valence electron, so A4. So we would expect there's going to be a total of 12 valence electrons in this compound. When we go to come up with our total or our structure, there better be 12 total valence electrons. So then we can also kind of look at, we have C2H4. So normally how these are written, the first atom is going to be the central atom. Here we have 2 carbons, so obviously both of them can't be the central atom. So what would normally happen is you would just put C, C. So hydrogens are the only thing else in here. Hydrogens can only form 1 bond. They always form exactly 1 bond. So as a result, we would expect that they can't be a central atom. They have to be kind of decoration hanging out around the outside of the molecule. They can't be on the, kind of middle atom of the molecule because they only form 1 bond, right? They kind of just hang off the side. So we have used, that's 1 single bond. So that would be 12 minus 2, there are 10 electrons left to assign. We can just kind of count how many electrons we need. Well, we know that each carbon atom needs to end up with 8 total electrons, octet. So it's going to generally form 4 bonds. We got some hydrogens that we can use, and we can just start adding them. H, H, H. So that carbon now has 1, 2, 3, 4 bonds. That'd be a total of 8 electrons. We have 1 more hydrogen. We could put it over on this carbon. And now we're done with atoms. Okay, and if we look, this carbon atom is good. It's got 1, 2, 3, 4 bonds. So that's good. This thing is stable, but this carbon atom only has 1, 2 bonds. And there are no more atoms that you can add in. If we look, we have used 1, 2, 3. We just put in 4 bonds, so that'd be 8 electrons. So we have 2 electrons left. We could think, well, maybe we could put a lone pair right there, but this carbon atom only has 1, 2, 3, 4, 5, 6 electrons. That's not a full octet. This thing is not stable. Generally, you do not want to be putting lone pairs on carbon atoms. That is not a preferred bonding pattern. This doesn't even have 8 electrons, so that's no good. And that's okay, right? We need to go back to the drawing board. That's not the Lewis structure. So we still have our base kind of carbon bonded to carbon. So now the problem we ran into was the hydrogen distribution, right? So maybe instead of putting all the hydrogens on 3 of the hydrogens on 1 carbon, we can separate them out. So I started with 12 electrons. I put in the 2 for the carbon-carbon bond. I had 10 more. I put in 1, 2, 3, 4 bonds to hydrogen. That's another 8. So now I have 2 more electrons. Those 2 other electrons can form a double bond. And so for C2H4, I'm going to have carbon bonded, double bonded to another carbon atom, and then they're each bonded to 2 other carbons. So again, we expect all carbon atoms to form a total of 4 bonds. So this carbon atom has 1, 2, 3, 4. This carbon atom has 1, 2, 3, 4. That's what we would expect to see. That's a predicted bonding pattern. So then if we want to look at formaldehyde, CH2O, so I've got 1 carbon, got 2 hydrogens, and I've got 1 oxygen. So that gives me 1 times 4, 2 times 1, 1 times 6. So 4, 2, 6, that'd be 12 total electrons. And so again, when I look at this, the first atom is almost always going to be the central atom. So that's perfect. I'll just put carbon in the middle, and then I'll just bond everything else to that. H, H, O. And we would expect that in general, these hydrogens are always going to have just the one bond, so these are already done. So if we go ahead and do our accounting, 12 minus 2, 4, 6. 6 electrons left. So when we're going about filling octets, hydrogen doesn't need 8 electrons, but oxygen does. So one of the ways we can approach this is just add enough lone pairs such that it now has a full octet. 1, 2, 3, 4, 5, 6, 7, 8. That oxygen atom is good, and importantly, that's all of our electrons assigned. So the oxygen atom has an octet, hydrogens don't, but they only end up with 2, so those all look good. This carbon atom is a problem though. This carbon atom only has 1, 2, 3 bonds. That's 6 electrons. So we need to kind of think about these electrons need to be rearranged. We have used all of our electrons, right? There are 0 electrons left. We expected there to be 12 total. There's 12 total here. They're just not arranged correctly. So what we can do is take this pair, instead of making it a lone pair, we can make it a shared pair. And then what we find is we have carbon double bond O, H, H, and there are still 2 lone pairs on oxygen. And now we can see that oxygen has 2 bonds, a single double bond, and 2 lone pairs, 1, 2. That's our expected bonding pattern for oxygen. Carbon is expected to have 4 bonds. We have 1, 2 single bonds, and then the 1 double bond, so 1, 2, 3, 4, for the total of 4 bonds on the carbon. And each hydrogen, as expected, only has a single bond. So these kind of tendencies, we always see carbon, it may form double bonds, it may form single bonds, but it will always have just 4 bonds and no lone pairs. Oxygen tends to form 2 bonds and 2 lone pairs. If we kind of looked at this, the carbon not having an octet is a problem, but it's almost easier to pick out that when we have those 3 lone pairs on the oxygen, that's not good. That tends to not be stable. That tends to not be stable, especially in neutral compounds, like formaldehyde or something like this. This isn't an ion. We would not expect to see something like an oxygen with 3 lone pairs and 1 single bond. Let's do one more, formic acid. So count electrons. I got 1 carbon, 2 hydrogens, and 2 oxygens. So 1 times 4, 2 times 1, 2 times 6. So what's that, 18? So I got 18 electrons. And so I know that's my kind of accounting that I want to do. I also know that this first atom's probably in the middle. So I'll go ahead and just put my carbon atom here. And, you know, generally I just attach everything else. H, H, O, O. And so if I want to do my accounting, I just put out 1, 2, 3, 4 bonds, each is 2, 4 times 2, that's 8 electrons I just assigned. So I got 10 more electrons. Start putting lone pairs on my oxygens, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. All right, so right now that would be everything. And this is a problem. I don't have enough electrons to even put lone pairs, or to get enough lone pairs to fill the octets on these oxygen atoms. So that's going to be an issue. This is going to be a real problem in terms of making this a stable molecule. So this is where we start to see some of the differences between organic compounds and what we would see with inorganic compounds that we would have seen in Gen Chem 1 or 1411. What we're going to start to see is these molecules aren't just going to be atom-centered, they're going to start to grow out in structure. So when we come to a situation like this, where if we try to kind of fill octets and we run out of electrons, that means we need to start moving atoms. And the easiest atom to move is always going to be hydrogen. So basically we could, in the previous on formaldehyde, we looked at moving electrons. Now what we're going to do is we're going to take this whole bond and move it onto this oxygen that didn't have a full valence. So what I can do is I can rearrange, again, I'm just rearranging electrons and the atoms, thereby that they're kind of attached to. So I can see I still have the 2 lone pairs on the oxygen. Here I've kept that oxygen the same, and I just moved that bond, instead of being between hydrogen and carbon, it's now between hydrogen and oxygen. And so now my 2 oxygens have octets, but this carbon atom doesn't anymore, right? It only has 1, 2, 3 bonds, but that's okay because I can also see that this oxygen atom has too many lone pairs. Take one of those lone pairs, turn it into a double bond, and then I can end up with the actual structure of formic acid, where my carbon atom has 1, 2, 3, 4 bonds, what we expect. Oxygen has 1, 2 bonds in a double bond, where this oxygen has 1, 2 different single bonds. This ends up being the Lewis structure that I would expect, the connections that I would expect. The carbon atom we can still think of as being in the middle, right? But now we're starting to see that, we have kind of bonds between non-hydrogen atoms that are both then bonded to hydrogen. So we can still kind of think this is kind of the structure of the molecule, where the hydrogens are just kind of hanging on the sides to fill out octets or to make everything balanced in the end. And so, we have kind of established rules that we've used for how to come up with Lewis structures. And we can always rely on those and use those, and we should use those. But we can also just start to develop kind of new intuition when it comes to forming organic compounds. Carbon, 4 bonds, oxygen, 2 bonds, hydrogen, just kind of fill out that decoration to make everything kind of fill out the octets where you need them, right? It doesn't have to be bonded necessarily to that first atom. It can be kind of spread around the molecule to fill all.
Even though we're looking at a small handful of atoms that bond in predictable ways when we're talking about organic molecules, there's still a ton of variety and a ton of flavors and different types of molecules that we can get in this types of classifications. We can get kind of the basic carbon and hydrogen, but you could also have, say, double bonds in there or triple bonds to change the properties. We can modify things like adding in little halogens or adding in oxygens that are single bonded or double bonded, nitrogens that are single, double, or triple bonded, right? And there's a lot of different varieties and a lot of different types of molecules that we can see that come out of this that follow kind of the procedure, that have a lot of different ranges of chemical properties, physical properties, but still they're all following the same basic rules that carbon's going to form 4 bonds, oxygen forms 2, nitrogen forms 3, hydrogen and your halogens form 1. And with that, the sort of kind of few ingredients, there's still a ton of flexibility, and it's really driven by the fact that you can get carbons to form bonds with other carbon atoms and get really big molecules out of it. So in order to kind of organize and understand molecules, we define what are called functional groups. And so this is going to mean some sort of pattern of atoms that you find within a molecule that describes particular properties or has kind of a certain kind of characteristics associated with it. And the idea is that this is going to allow us to organize organic compounds into families. This is how we're going to name organic compounds, kind of the rules for naming compounds. And it's because these functional groups, these few set of atoms within a molecule, are going to have unique chemical properties, physical properties that are going to be transferable between molecules. So we're going to talk about some and talk about how to recognize some, and a little bit about what some chemical and more physical properties of those functional groups. So these are the functional groups that were shown up here. We're going to walk through these, but we just want to kind of get an idea of what we're looking at. Again, this is the idea of functional group is a small handful of atoms within a molecule. So for example, just OH bonded together. That would be part of a bigger molecule where the OH is just a part. And so the OH is the functional group, then CH3CH2OH is the whole molecule containing that small functional group, that OH pair of atoms. And so this functional group corresponds to a family, the alcohol family. And so all molecules that contain that functional group are alcohols, and they have their properties associated with alcohols. And we can see, so that's just the case of, say, small handfuls of atoms, amines, or it can get much more complicated, like, say, for example, esters, where you have, say, carbon, double bonded to oxygen, and single bonded to another oxygen, where this is kind of a pattern within a bigger molecule that's kind of holding it together. We can kind of look and see that, like, the OH up here is kind of on the side, kind of hanging off the side of the molecule, whereas in the case of, say, this ester down here, it is a central part of the molecule, right? It's structural to the molecule. And so we'll walk through these different types of functional groups and kind of some of the properties they imply through the rest of these videos dealing with chapter 20.
All right, our final week. Got a participation due Tuesday, and the midweek homework. Don't want to forget that in all the excitement covering this first set of videos that started chapter 20. On Wednesday, we'll have our lab final. No pre-lab or anything like that you need to do. You can just show up and take a look at that. There is the page of potential topics that you can find on Blackboard that are relevant. We'll have a second set of videos later this week, weekly homework, and then your lab presentation. If you have not given it yet or turned in your video, you want to make sure you get that turned in by December 2nd, or just do it live whenever we're scheduled to do it. Otherwise, welcome to chapter 20. Welcome to week 15. The end is close. I'll see you in the next video.